The idea of a rivet is really very simple. It's kind of like a nail with a head on both ends. The rivet, by definition, is a rod or a length of material that goes through sections and then is upset or bulged over on both the top and the bottom, and that makes the clamping action that holds it together. I'm going to do a standard rivet here. Any piece of metal can become a rivet. In this case, I'm using a piece of wire that goes through holes that I've already drilled in these two pieces of copper and brass. It's critical that the wire make a very snug fit as it goes through. If the wire is so small that it wiggles in the hole like this, it won't make a sound rivet. A wire of the correct diameter fills the hole completely. And now I will snip that. And then file it. The snippers always leave a pointed end, and we don't want that. So I'll file it off till it's square. And at this point, I'm also paying particular attention to the length of the rivet. The idea is to have half the diameter of the wire projecting on each side. In other words, if you were using a wire a millimeter in diameter, you'd want to have half a millimeter of metal extending out here and half a millimeter extending in that direction. I'll be working on the surface plate, or bench anvil, which is a small piece of polished steel. And I'll be using a riveting hammer. This is a small cross-peen hammer. The cross-peen refers to this wedge-shaped end. That allows me to control the direction in which the metal will move when it's hit. I want to be careful that I don't press it all the way down. That leaves too much rivet showing on this side and nothing on the underside. Instead, I'll raise the workpiece so it's hovering above the bench plate, allowing a little bit of the rivet to project below and a little bit above. I'll then strike it with the cross-peen hammer. Obviously, force is not necessary. This hammer, though it looks like a toy, is a very effective tool. It's marksmanship that counts. As I strike, the round wire is changed in shape and becomes an oval. The next step is to turn the whole assembly 90 degrees and hit crossway to what I was doing before. So you might think of it as making an X on the top of the wire. Again, this process is called upsetting. That word refers to the activity of pressing metal down on itself. Having created that upset head, or the mushroom head, on one side, I'll now flip it all over and repeat the process. Typically, rivets or other cold connections are done late in the process. Here, of course, I'm just working on sample pieces, but if I was making a finished piece of jewelry, I would have probably worked these pieces all the way through the conclusion. That is, stones would be set, the patina, the color would be in place, the edges would be smooth, and so on. That's usually done because it's easier to work on the pieces when they're separate than it is after they're assembled. Because the piece is nearing completion, it's a good idea to avoid extraneous hammer marks, which will be scars that have to be worked off later with sandpaper or polishing. And I do that by anchoring my hand out here. Rather than have my hand free to move around, it's pivoting. The heel of my hand is resting on the bench so that this becomes a very robotic, machine-like activity here. Once the rivet has been properly pressed down and the two pieces of metal are well joined, then I'll flip the hammer over and use this flat face. That has the effect of smoothing out the little lines that are left by the cross-peen end of the hammer. The rivet can also be finished by polishing or shaping with a beading tool. Now you'll notice in this case that I've drilled additional holes in the copper, but not yet in the brass. First thing to notice is that you always have to have more than one rivet, because one rivet will still allow the pieces to rotate, unless, of course, that's what you want. It would be tempting then to originally hold the pieces together and drill a bunch of holes. Not a good idea. Even when you try to be very careful, it seems inevitable that somewhere in the process, between the second and third hole or the fifth and the sixth, somewhere, the two pieces slide a little bit, and all it takes is a little bit to throw you off. The effect then is you get one or two rivets in position, and when you go to put in that next one, the holes don't line up, and it's a very difficult situation from which to recover. So instead, I'll drill as many holes as I want in one piece and a single hole in the bottom sheet. A rivet here still allows the top to rotate. I'll drill a second hole opposite the first and form a rivet there. Now the pieces are locked in position and the rest of the holes can be drilled. It's hard to overestimate the value of rivets. Not only can they be used to join pieces of metal without the introduction of heat, but they're handy for cases where heat is not an option. For instance, when you're attaching wood or shell or stone. What I've demonstrated is a very straightforward and usual case, two flat pieces being joined. But a lot of times you'll have to come up with a particular situation because of the shapes with which you're working. Here's an example. In this case, I fabricated a cap out of sterling, which I'm joining onto a leather strap for a necklace end. And I want to put a rivet right down through here. But it's impossible for me to set this down on a flat surface because of the two wire bands on either end of the cap. If I strike it here, there's no resistance beneath, and hence there will be no rivet head. In a case like this, I have first drilled a hole and fed a wire through it, and then I've gripped a stamping tool here in the vise to serve as a temporary anvil. You can see when I set this down that the rivet head is in contact with the anvil. From here, riveting proceeds as usual. Another variation on rivets is the tube rivet. In that case, a length of tubing is substituted for the solid rod and used to join pieces of metal together. An advantage of the tube rivet is the fact that it takes less stress to curl the edges over. For that reason, it's recommended for delicate situations, as in the setting of an enamel or a shell. Another advantage of the tube rivet is that there's a perforation that runs through the join. This can be used to attach a moving part, or, for instance, as in this can opener, it makes a nice place for a thong. The making of a tube rivet exactly parallels the standard rivet that we looked at earlier. A length of tubing is sawn off. Again, it should project about a half a diameter on either side of the sheet. It's then laid into position, centered, and instead of hammering, any sharp tool like this scribe can be used to begin the curling over process. The scribe is laid gently into the tube and rotated like this, which has the effect of curling it outward. After one side is started, you'll flip it over and work on the other side. And you'll need to go back and forth 3 or 4 times anyway. You'll be able to see the edge as it curls outward and grips the two pieces of metal together. I'll then use a hammer to finish off the joint and set the rivet in its final position. The tube rivet is finished by pinching it between a pair of dapping punches like this. A light tap is all that's needed. Whether you work in large scale or small scale with precious metals or base metals, I think you'll find lots of uses for cold connections. At the same time, a lot of jewelry making involves soldering, and you're going to have to learn how to control it. That's where we should turn our attention next.